Welcome back to OGLDEV. I guess it's quite clear that there is a limit to the complexity of a manually created model. A pyramid is okay, a cube is also okay, but when it comes to modeling something from the physical world, you need some help there. That's why we have software like Blender, Maya, 3ds Max, and many other tools that allow you to create models in a sophisticated 3D environment with lots of supporting tools that help the modeling artist create the amazing 3D worlds and objects that we are used to in modern games. The modeling software takes care of calculating the position, texture coordinates, and any other vertex attributes that you may need. It also groups the vertices into triangles and manages the corresponding indices. And finally, the modeling software saves all this data to files so you'll be able to load the model in your game or application and manipulate it using OpenGL or any other 3D API. It will probably not surprise you that since there are many 3D modelers, we also have lots of formats for the model files. Here's a partial list. So if you want to load these model files into your game, you can either write a custom loader yourself or use an existing library for that. If you like writing everything from scratch, then you're welcome to write such a parser on your own, but my recommendation is to go with an existing solution because it will save you a lot of time. In this video, we're going to use the Open Asset Import Library, or SIMP, which is a free and open source library that is very easy to use and supports many file formats. SIMP takes care of parsing the model file, which, by the way, can be text or binary, and loads it into its own native data structure in memory. What we need to do is to use this data structure in order to populate OpenGL vertex and index buffers, load any textures that may also be present, and set up the layout of the vertex attributes. Let's start by installing SIMP, and we have several options here, depending on the operating system. I'll include the instructions for everything that you're going to see in the video description. If you're on Linux Ubuntu, you can simply execute the following command to install SIMP. If you want to build SIMP yourself, you'll need to clone the following repo. cd into the new directory and execute cmake --. If you don't have cmake installed, you can easily install it using sudo apt install cmake. At this point, you may run into various difficulties, mostly due to missing packages. Let me know of any issues in the comments and I'll try to help as much as I can. You can also use the support forum on the GitHub page. If cmake completed successfully, you can execute make and then sudo make install to complete the installation. Now you need to integrate SIMP into your build process. As you probably know, I'm using simple bash scripts to build my sources. In these scripts, I'm using package-config to get the build and link parameters, so all I need to do is to add SIMP as a parameter to the command package-config --c flags to get the include directory, and package-config --libs to get the link command. The results of the two commands are provided as parameters to G++ below. Package-config is very handy because its behavior is tailored to the distribution that it is running on, which makes it very flexible. On Windows, you also have two options. You can use the binaries provided with my source repo, or you can build the source yourself. Unfortunately, it seems that pre-built binaries for Windows are no longer available from the SIMP website. Okay, so if you want to use the binaries that I've created, you can go to the OGLDEV directory, go to Windows down here, and in the lib directory you will find this file simpvc142mt.lib. That's the library that you need to link against. It's a release build of SIMP, and you also need the DLL for runtime, which is in this directory, DLL. It's the same file, just with the extension DLL, okay? And you will also need all the headers that we have here at OGLDEV/include. We have SIMP, and that's all the headers of this library checked in right here. That's the latest version at this time. Now, if you want to build the sources yourself, you need to check them out using Git. I'm using Tortoise Git, and I've explained how to install it in a previous tutorial, the one about Windows support, so you can find it there. So what you need to do is right-click in some directory and then git clone, And here's the address of the website, which by default will go to this SIMP directory. Now I don't need to press OK because I already got it checked out right here. So let's go inside. And here you can shift right click and go to open a PowerShell window here. And you will also need CMake install. So just type CMakeLists.txt and run it. And it will generate the Visual Studio solution file, which we can find right here, simp.sln. So let's open this one. And here you can select whether you want the debug or the release version. As I said, what is checked into the OGLDEV source repo is the release version, and make sure that you're using x64. And then you just need to do build and rebuild solution, okay? Okay, the build is complete, so we can go back to simp/lib and select debug or release, whatever you use to build. In this case, release, so we have this file here, which is exactly the one which is checked into the OGLDEV source repo, and also in /bin, we have the DLL, okay? Okay, now go to your project, right-click it, Properties. Let's go to Linker and Input, and here in the additional dependencies, we have the SIMP lib file. You will also need to make sure that in C++ general you have the include directory here as the additional include directories. Now, I've already got this directory from all the previous projects, which is going up 3 directories, and include from the location of the project. Okay, so if we go to the location of the Visual Studio project file in OGLDEV Windows, OGLDEV VS 2019, we have the project right here. So we're going up 3 directories, and here we've got include, and here's the SIMP headers. So when we include the headers, we can simply write this directive right here, because this references the include directory that we just saw. And we also need to make sure that the DLL file can be accessed during runtime. So let's go to the project properties again and go to debugging. And here we can see that I've added the location of the DLL directory right here. So now we can run it. Now let's dive into the code, and I will explain the structure of SIMP as we go along. Okay, so first I created a class called BasicMesh that represents a model loaded using SIMP. This class is declared in OGLDEV BasicMesh.h in the include directory. We have several public and private functions here, as well as a few private variables. We'll revisit these items as we go through the class. Now let's go to the implementation of this class in OGLDEV BasicMesh.cpp in the common directory. The first function I'd like to review is LoadMesh, which is a public function that takes a file name as a parameter and serves as the top-level entry point for the entire loading process. The first function call inside this function is to the clear private function. This function clears all the internal data structure of the class, allowing you to reuse the same class object for loading a different model. We're not going to use this capability in this tutorial, so I'll just skip it. Next, we generate and bind a vertex array object for the current model. We've covered VAOs in the previous tutorial, so make sure you watch that for more details. Next, we generate 6 OpenGL buffer objects. mBuffers is a private array of 6 unsigned integers. In this tutorial, we're going to see a different method of storing vertices. What we've been using so far is a method known as array of structures, or AOS. The core element in this method is a structure that contains vertex attributes such as position, texture, coordinates, normals, etc. For storing multiple vertices, we have an array of this structure, hence the name array of structures. This array is loaded into the OpenGL buffer, which means that the attributes are interleaved there in the exact same way as in CPU memory. The second method, and the one that I'm going to demonstrate today, is a structure of arrays, or SOA. Here we have a separate array for each of the attributes, okay? So we have an array of positions, array of texture coordinates, and so on. We can group these arrays together in a single structure, hence the name structure of arrays. The arrays must all be of the same length, so in order to access all the attributes of a single vertex, we need to use the same index to access each of the arrays. OpenGL allows us to use both methods to build up our 3D objects. We use an enum to access each buffer by its name rather than an obscure number, so the first buffer is the index buffer. We have the position at index 1, texture coordinates at index 2, and normal at index 3. Normal vectors are required for lighting effects. For now, this is just a placeholder, so if you're writing this code yourself, you can drop it. The last two buffers, WVP MatVB and World MatVB, are also placeholders. They will be used in the future when we get to instancing. Back to LoadMesh, we can see that we're initializing all the buffers in a single call to glgen buffers. By the way, array size in elements is a handy macro for calculating the number of elements in an array by dividing the size of the array by the size of the first element, which must always exist. In order to access the services of SIMP, we define an object of the importer class, which is defined in the SIMP namespace. To get this compiled, we must include 3 files from the SIMP include directory: importer.hpp, scene.h, and postprocess.h. To actually load a model, we call importer.readFile, passing in the model file name and the list of SIMP flags, which is wrapped inside this SIMP load flags macro. These flags allow us to modify the behavior of SIMP, so let's quickly go over them. First, we have the triangulate flag. Many modeling tools allow you to build models using polygons with more than 3 vertices. We must use triangles, so this flag tells SIMP to split these polygons into triangles. GenSmooth normals is for lighting, so let's skip it for now. FlipUV flips the texture coordinates along the V or the y-axis of the texture. This is something that you may need to play with to make this work with your models, because some modelers will allow you to control this when exporting the model. And finally, we want SIMP to join identical vertices and adjust the index buffer accordingly. This will save us some memory. There are many more flags available in the SIMP postprocess.h header, and you can find the full documentation online. This is actually one of the reasons why SIMP is so flexible. If readFile returns null, then the call has failed and we print the error using importer.getErrorString. Else, we get back a pointer to an object of the aiScene class, and we call init-from-scene to continue the initialization. aiScene is the top-level data structure in the memory representation of the model that SIMP created. As usual, before we leave this function, we unbind our VAO from the OpenGL state. Now let's continue with init-from-scene, which is defined below this function. The way that the aiScene is structured is that it matches the behavior of most modelers that enable you to split up the model into subcomponents. This allows you to apply some transformation on one component without affecting the others. So you can have a head, an arm, a sword, and whatever. If the model is split into subcomponents, SIMP creates an aiMesh structure for each component. This aiMesh contains all the vertices and indices of that component. The number of aiMesh structures is given in the mnummeshes variable of the aiScene class. We reserve a matching number of elements in our private variable meshes, which is a vector of BasicMesh entry. BasicMesh entry contains a few variables that we will need to maintain for each aiMesh, such as the number of vertices, base vertex, etc. We're going to see these soon. aiScene can also contain textures, and SIMP wraps one or more textures in something which it calls materials. These are stored in an array of aiMaterial structures, and the size of this array is given in mnummAterials. We have a matching vector of pointers to our texture class, so we reserve space there accordingly. Now here's the plan. We're going to stack up all the vertices and indices from all the aiMesh structures in the buffers we've just created according to their type, index, position, texture coordinates, etc. However, each aiMesh may use a different texture, but we can switch textures in the middle of a draw call. This means that we need to launch a draw call for each aiMesh separately, and this will give us the opportunity to switch textures as needed between draw calls. This also means that we cannot use GLDrawElements because this function only draws vertices from the beginning of the buffer. We need a more sophisticated function that allows us to draw from different offsets within the buffer, and OpenGL provides us with such a draw function. Okay, so in order to actually allocate space in our index and vertex buffers, we need to know how many vertices and indices there are in the entire scene object. Unfortunately, these are not readily available to us, so we need to actually count them. We do this in the private function count_vertices and indices, which also updates the meshes array. We just need to loop over the elements in the meshes array that we've just resized. For each element, we copy the material index from the corresponding aiMesh. We calculate the number of indices in the current mesh by multiplying the number of faces by 3, since after triangulation all the polygons are now triangles. The base vertex is the index of the first vertex of the current mesh in our global buffers. To calculate it, we increment num_vertices by the number of vertices in the aiMesh. We calculate the base index in a similar fashion by incrementing num_indices by the number of indices of the current mesh that we've just calculated. So, for example, if we have 3 meshes with 100, 200, and 50 vertices, then the first mesh is at offset 0, the second mesh is at offset 100, and the last one is at offset 300. When we exit the function, both num_vertices and num_indices contain the totals for each type. When we're back to init from scene, we call reserve space with the 2 counters. This function allocates space in 4 vectors for the positions, texture coordinates, normals, and indices. These vectors are private members of the class. They will be used to accumulate all the vertices from the aiScene structure, so we can load each OpenGL buffer with a single call to GL buffer data. Back to LoadMesh, we call init all meshes, which simply traverses all the SIMP mesh structures and calls init single match for each one. In this function, we actually populate the vectors that we just saw with vertex and index data. We do this by going over all the vertices in the aiMesh and extracting the position, normal, and texture coordinates from their respective location in the aiMesh. Notice that these items are represented by SIMP AI Vector 3D, which is very similar to our vector class. In the case of the texture coordinate, we must also check that it exists, and if not, use a 0 vector instead. We can now populate our vectors with this data. Also notice that in the case of the texture coordinates, we only use the x and y out of the 3D vector. Populating the indices is very similar. The aiMesh contains an array of triangles called mFaces. Each AI face structure contains 3 indices, which we need to push into the indices vector. The next function that init from scene calls is initMaterials. This is where we allocate GL textures for the images in the model. The image files are stored in the same directory as the main model file, so first we need to extract the directory of the model file. This is done by a simple parsing of the last / character. We can now traverse the materials array in the SIMP scene. A material is basically a container for multiple textures, and it may contain diffuse, specular, and ambient textures, as well as stuff like a height map, normal map, and etc. These are required for more advanced stuff like lighting. For basic texturing, we just need a diffuse texture, so we check whether it exists by calling getTexture on the material with the AI texture type _diffuse enum in the first parameter. The second parameter is 0 because we only want the first texture. The third parameter is an address of an AI string variable where the path of the texture will be returned, if it exists of course. Right now we don't need the rest of the parameters, so we have nulls there. If the call was successful, we construct the full path of the texture file. Inside the model, the path of the texture is relative to the location of the model file. Now we can create our texture object as usual and load it. Let's go back to init from scene for the last time, and the final call here is to the private function populate buffers, and this is where we prepare stuff for using SOA. We start by binding the position buffer to the GL array buffer target to make it current. We load the data from the vector into the buffer by calling glBufferData. The number of bytes is obtained by multiplying the size of the first element by the number of elements in the vector. The base address is the address of the first element, and we use glStaticDraw because we don't plan on updating the buffer again. Next, we enable the vertex attribute for the position. At the top of this file, we have macros for the location of the 3 vertex attributes. It's not the most robust design because we must keep this in sync with the shader, but it will do for now. Next, we configure the layout of the position buffer by calling glVertex_pointer. Again, we use the macro for the index of the attribute. We have 3 floats here, glFalse for no need to normalize, and the last 2 parameters are now 0. Previously, we had to put here the size of the entire vertex structure and the offset of the current attribute inside the vertex. Since the positions are packed one after the other, we can now put zeros here because the driver already knows everything from the 3 floats. We repeat the same process for the texture coordinates and the normals, and every time we call glVertex_pointer, the driver stores the address of the buffer which is currently bound to glArrayBuffer for the current attribute. This enables each attribute to come from a different buffer. Okay, so SOA, structure of arrays. Finally, we populate the indices. Just remember to use glElementArrayBuffer for the target here. Congratulations, we are done with uploading the model. The only thing that we have left here is of course the render function. We start by binding the VAO of this model. This brings in the vertex layout that we've just created. Next, we traverse our internal meshes array. We get the material index and we check whether we have a corresponding element in the texture array because there may be a material without a diffuse texture. If there is a texture, we bind it. Color texture unit is simply a macro for glTexture0 that I keep in OGLDEV engine common.h. I'm using this file in order to keep the tutorial somewhat consistent. Now comes the interesting part. Instead of glDrawElements, we use GLDrawElementsBaseVertex that allows us to draw subregions of the vertex and index buffers. The first parameter is glTriangles as usual. The second parameter is the number of indices of the current mesh, which we've calculated when we loaded the model. Next is the data type of the index, unsigned int in our case. Next is the offset to the first index of the current mesh in the index buffer. So we multiply the base index of the current mesh by the size of an unsigned int in order to get the offset. We also need to cast it to void pointer. I think this is due to some historical issue with this function. The last parameter is the base vertex for the current draw call. You see, the original indices that we got from SIMP started at 0 in each aiMesh structure, but we decided to stack up all the vertices in a single buffer per attribute. This messes up the indexing. One solution would be to adjust each index based on the starting position of the mesh in our single buffer. A more simple solution is to use this last parameter here as a base vertex. This number will be added to each index so that it will match the offset inside our buffer. For example, let's say that we have 2 AI meshes. The indices of both meshes start at 0, but each mesh obviously refers to its own set of vertices. We stack up the 2 vertex groups one after the other, and let's say that the size of the first group is 100. So the base vertex for the second group will be calculated as 100. When we render the second group, we will pass in 100 in this last parameter, so that index 0 will become 100, index 1 will become 101, and etc. So we have a subset of indices that start at some offset inside the index buffer, and to each index, OpenGL will automatically add whatever we put as the base vertex. All these elements were already calculated when loading the model, so they are now ready when we get here. Okay, so we have a series of draw calls here. Each draw call uses a subset of the index and vertex buffers, and before each draw call, we have an opportunity to switch textures. Now let's see the changes in the main application code. In the tutorial 18 class, I got rid of all the VBOs, VAOs, and index buffer that I used to keep around here, as well as the world transform object. Instead, we just need a single pointer to BasicMesh. In the init method, we need to call LoadMesh with the path of the model file. In the main render function, we perform all the transformations on the world trans object that we have in the BasicMesh class. So if we have multiple meshes, it makes it simple to keep the transformation of each mesh inside its own object. Also, instead of calling glDrawElements, we just need to call the render function on the mesh object. This is basically all we need to do here. Now let's build and run this. Okay, so this looks like a spider, but there's obviously something wrong here, right? The problem is that I haven't enabled the depth test. Without it, the frame buffer works like a regular canvas. So whatever color you use last, that's the color that you're actually going to get on the final screen. With simple stuff like the cube, we couldn't see the problem, but with more complex models, the problem is evident. I discussed the depth buffer in a previous episode, so I won't repeat it here. By enabling the depth test, we make sure that the closest pixel is rendered, regardless the order of rendering. We do this by calling GLEnable with the GLDepthTest macro as a parameter. We must also clear the depth buffer on every frame, else it will contain garbage data from the previous frame. So in the main render function, we add the GLDepthBuffer bit with the bit mask that we provide to the GLClear call. Okay guys, you can now go ahead and try to load different models that you find for free online, or that you create yourself if you know how. I can't guarantee that this code is bulletproof and will work for every model. It probably still contains some bugs. Please let me know if you run into a problem. I hope you enjoyed this episode. I was actually not sure whether I should do such a deep level code walkthrough, so please let me know if you found it useful. If you did, please hit that like button and subscribe. You can also support this channel at patreon.com/OGLDEV. Thank you for watching, and I will see you in the next tutorial.